last time I basically showed you that we can think of ideals in some sense as numbers. And so we can define addition and multiplication in terms of these sets of numbers, right? I'm talking to my brother, and I guess maybe I'm not entirely on board with him philosophically. He said that when he teaches these things, one of the things he tries to get across to the students is that you're not really changing the object you're working with. He says you're changing your notion of equality. So, and I kind of see what he's saying, because if you look at how we define ideal, like arithmetic, how do we, I plus A, I plus B is equal to what? It's I plus A plus B. So you're still adding A and B, same way you were before, right? Or I plus A times I plus B. How do you multiply? It's I plus AP. So it's still the same old stupid multiplication. It's maybe the same old, not stupid, wonderful addition. And so Bill says, a key intuition is that when you're working with ideals, you're not really changing the operation as much as you're changing the notion of equality. I think I see what you're saying, if you really look at what we did. At the same time, I kind of disagree because I feel like we're working with sets instead of numbers. So, I don't know. I think, like you said, philosophy, so you could differ. Okay, so the conjugate ideal is what? So this brings us to section 6.6. Listen to me. Section, what section is this?
12.8.
12.8. Then I wishful thinking, we're not there yet. Section 12.4. See what you did there. Let's try. Section 12.4. And here's our definition. If A is an ideal, okay, and let us realize, let us just state for today, R is the ring of integers in ring of integers for some imaginary quadratic field. So basically, you take the rational numbers and you adjoin the square root of d, where d is less than 0, and it's square root of 3. That's our context. Okay, so when I talk about an ideal, I'm really talking about an ideal that is appearing in the ring of integers over an imaginary quadratic field. Which is not to say that some of these ideas couldn't be abstracted from this context. It's just to say that that's our context, okay? I don't mean to say that this is the only thing you can say these things for. Many of these arguments probably could be ripped off for a more general context without much work. If A is an ideal, then the conjugate ideal, A bar, is equal to, well, guess what? It's C bar such that Z is an A. So basically, the reason to study the conjugate ideal, and we've already seen examples of this, like where was a place we saw a conjugate ideal? Do you remember, for example? We factored, what was it, over Z in Z5? Remember what we had? The ideal, I'm trying to remember, was it?
2 and 3.
Yeah, which one was the one that had the distinct factors?
2, 1.
2, was it 2? It was either 2 or 3. One that wasn't squared, one that was...
Oh, 3.
3, okay, so 3 was what was it? 3 was equal to?
Well, I don't know what you're asking. 3. Okay, 1 plus square root of -5. And 1 minus square root of -5, but there's a 3 in front of that. You see what I'm saying?
3 in front of that.
It's like 3 it's like almost like an ordered pair.
Most annoyingly, I have left my book back in my office today.
you like to borrow one?
Yes, I would at some point. Oh, thanks.
Go ahead, Sharon.
You guys are funny.
No, but anyway. You should go to the Gaussian integers. It's fun joke time. There's a nice little joke there for you. See, this is why I was gonna offer my book, but you wanted your book. This is a joke.
So what are your enemies like, Sharon?
What?
So what are your enemies like?
I don't have
Okay.
any.
Where was this that we had, that was in section 12, wasn't it? Yeah, 11 words.
Look, I just don't know how to tell them this.
Ah, finally. It was on page 215, it was 3. So, and you're right, there was a 3. So it was 3, comma, right? 1 plus 0.5, 3, comma, 1 minus the square root of minus 5. I'll take it again later. But.
Okay.
So this would be like A, right? This would be like A bar. Now, remember this notation means is this is actually equal to what? It turns out that the ideal generated by 3 plus the ideal generated by what? 1 minus, well, minus 3 minus 5. I think that the conjugate of the sum is the sum of the conjugates. I haven't proved these things though, so if I'm wrong, let me know. So anyway, I think that would be an example of the theorem we're about to prove, which is a really nice, simple result for an ideal of a. We know that the ideal of a in the quadratic, in the ring of integers of our quadratic imaginary field, it need not be principal, right? It doesn't have to be generated by one thing. Like this one is not principal, right? It's generated by 3 and this other thing. And this also is not principal, right? Because it wasn't the interesting thing about ZHO squared minus 5. Is that there were 2 kinds of ideals, 2 shapes, right? The whole thing and these sorts of things. So it is non-principal ideals. But you notice that the product of the ideal and its conjugate gives you this, which is a principal ideal because it's generated just by 3. Right, so what does this notation mean? You guys remember? This is really just a set 3R such that what? R is an element of, R. So, in fact, this is a theorem that this holds in general for a quadratic imaginary field, an ideal in there. So here's the theorem. If A is subset of R, and A is not equal to 0, then there exists K in the integers such that A bar, which by the way is equal to A bar A, because we're in the commutative context here. Anyway, that is just equal to K. So we can't assume that every ideal is generated by just one thing in the ring for an arbitrary ideal. However, if we just take that ideal and we multiply by its conjugate, then we can. So while there are non-principal ideals, they're always really, really close to a principal ideal by simple multiplication by the conjugate. This is the calculational principle that powers everything that's done in the last sections of chapter 12. This is what makes things work so nicely. Now, at this point, I think I'm going to save us from, well, no, fine. Let me see how much off track Sharon's got me. Oh, we're in okay.
What? You said, let me see how much Sharon got after.
Hey, you got me off track
How?
with your joking, your digression.
I did not digress.
Right. All right, I will stop accusing Sharon of things she has not done.
Thank you. I am making enemies.
So, let A be a non-zero ideal, right? In R, by lattice property, which I think was section 11.6, if memory serves me correctly. We know that we can write A is equal to what? M alpha plus M beta, where M and N are integers. So that makes it, that is to say that A is a lattice with integral basis alpha beta. Right? And then what's the conjugate ideal? Well, M and N are just integers, right? So A conjugate, you could even, use the same parameterization if you wanted, just M alpha plus M beta. Because the conjugate of M and N is just M and N again. So I mean, taking the conjugate of an arbitrary element just gives you that. And so, but you can see that the conjugate ideal is what? It's also a lattice. No surprise there. That make a decent test question. Given that A is ideal, prove that A conjugate is also an ideal. There's so many of these stupid little ideal questions, Anyway, I hope you see that as you work on the homework that's due Thursday.
Friday.
Oh, Friday.
Oh, boy.
There's too much going on.
So
Friday?
sorry.
That's what it says.
Oh. Well, that was nice. Why did you do that?
Because you put linear horses in
Oh.
End of physics test.
So nice. And physics.
Oh,
Get
physics
over
test?
all directions.
You
Yes.
guys aren't taking physics with me.
I'm taking
Oh,
physics
you
with you.
But, I mean, come on, that's going to be an easy physics test.
There's no such thing as an easy
Is it?
physics test.
There's such thing as
Words
if you don't go in a
test.
sentence together.
No, there is. It doesn't happen.
What?
I will prove you wrong.
Hey.
By giving us a really easy, really
I will
easy
prove you wrong.
Hey.
I'll prove you wrong.
Hey.
One
Hey.
question.
Hey.
You
Hey.
can get your
Hey.
favorite. You're welcome.
I'll talk to you on Thursday.
Just one question.
You have to actually bet something though, so he sticks to it though. Like word.
So if we calculate the product of these ideals, A bar, right? We define that, like, I think a few classes ago now, right? That's defined by taking sums of products, one thing from A, one thing from A bar, right? So you have to multiply. Basically, this is just things. I mean, what it boils down to is it looks like stuff like this: M alpha plus N beta times, let's say, A's got a letter. I don't know, L alpha bar plus. Okay, yeah. Oh, sorry, thank you. A beta bar. So that's it. And technically, I should take sums of such things, but I think there's no loss of generality here. So you guys can deal. Integers, right? I mean, again, technically, I should take sums of these things, but you can pretty much see that they're going to regroup to just the same fundamental product. So there's really no loss of generality in just taking one product. When you multiply this out, what do you get? You got stuff like, I'm just going to use combined. So you got M, L, alpha bar, plus M, K, alpha beta bar, plus N, L, beta alpha bar, plus N, K, beta beta bar, right? And so you could really just call this C1, C2, C3, and C4 were what? C1, C2, C3, and C4 are what? they're just integers, right? So if you look at it, what you really have are these generators, alpha, alpha bar, beta, beta bar, alpha bar, beta, alpha, beta bar. And you can find, let's see, let's consider there are real elements in here. What are real elements? What is real? Oh, okay, in a bar. So we'll make the question a little bit easier. So for example, alpha, alpha bar. Take the conjugate of that, you get alpha bar bar, otherwise known as alpha alpha bar, right? I mean, so that's real. Likewise, beta beta bar and alpha beta bar plus alpha bar beta. If you conjugate that, you get alpha bar beta beta bar plus alpha bar plus beta bar, which of course is alpha bar beta plus alpha beta bar, which is just what we started with the terms, the sums. I mean, of course you can compute addition, right? And multiplication is commutative here, so we can move things around. All right, so great. But I would remind you, so these in particular, so we have alpha alpha bar, just to recap, beta beta bar, and this sum of alpha bar beta plus alpha beta bar. These are all real. These are real quadratic integers, right? But do you remember what we proved back in section 10.4? Well, actually, I'm not entirely sure it was 10.4, but we did talk about this before. We proved that if the quadratic integer was real, it was actually just an ordinary integer. So in fact, I can say not just that these are real quadratic integers, this implies that these are indeed just the plain old garden variety integers. That was one of the reasons when we were first introducing the algebraic numbers and then the algebraic integers afterwards in terms of zero sets of monic polynomials with integer coefficients. Well, one of the reasons we said that was a reasonable definition is because if an algebraic integer was real, it forced it to be a regular integer. We proved that. So, because it'd be kind of weird if like real algebraic integers would be like integers and also this other batch of numbers that are in the reals. That would be kind of a weird terminology. That does not happen, thankfully. Okay, so then what can you say about the greatest common divisor of these guys? GCD of alpha alpha bar, beta beta bar, alpha bar beta, plus alpha beta bar is also an integer, right? Because the greatest common divisor of integers is again an integer. And by a slight extension of Buzow's theorem, you can say that in fact there is m alpha alpha bar plus n beta beta bar plus L, I guess, alpha bar beta plus alpha beta bar, which is equal to what? Well, I would say 1, but I can't say that. I don't know about that. But I could say k, right? And I can say k is equal to the GCD of these three guys. Okay. That is exactly the k that we're going to argue generates the product of A and its conjugate. This is the k which is the generator of the principal ideal formed by A, product of A and A conjugate. Okay. Now what do we have already then from this construction? So is K an element of AA bar? What have I done?
Clear.
Clearly? What by clearly not clear? There's a certain irony in that. Or it's just the general use of the word clearly here. It's a tradition. So, so the greatest common divisor is built from what? It's built from sums of integer multiples of these things. So it's clearly in here. So K is an element of AA bar by construction. So if K is an element of AA bar, what does that mean? Then the ideal generated by K, because it is also a subset of AA bar. Right? So conversely, what do we need to show? Yeah, we seek to demonstrate that A bar is a subset of the ideal generated by K. All right. In other words, we need to show that K divides alpha, alpha bar, beta, beta bar, alpha, beta, bar, beta, and alpha, beta bar. Anyway, here's the proof. Okay, so note K divides alpha, alpha bar, and K divides beta, beta bar by construction. Right? Because K is the greatest common divisor of alpha, alpha bar, beta, beta bar, and alpha bar, beta plus alpha, beta bar, so clearly K is a divisor of alpha, alpha bar, and beta, beta bar. Do you guys agree? Whoa. Okay. But what else? And then what he says is this. He says if alpha beta bar over K and alpha bar beta divided by K are elements of the ring, right? Then K divides alpha beta bar and K divides alpha bar beta, which then would imply, what would that imply? That would imply that A bar is a subset of K. All right. Why would that imply that, if you have because if you have divisibility by all four of these elements, when you write that divisibility in terms of multiples, it means that anything in AA bar can be written as a multiple of K, which then proves that. So we've got this big hanging if here. How do we decide about that? Well, here's what he does. He says observe the following. So what he does is x minus alpha beta bar divided by K. Every once in a while I present something in class and I go, I'm sure I would have come up with this. And this is kind of obvious. This to me is not obvious at the moment. Like why? But I guess, on the other hand, I guess it's the kind of thing you have to do. Because how do you define something being an algebraic integer? It has to satisfy some monic polynomial, right? It's a quadratic integer. It's defined by a quadratic, so I guess this is the natural thing to look at. What did I do?
Oh, nothing. I can't see. Sorry.
Oh, I'm sorry.
No, I'm wearing my glasses.
Oh. So all I've done is x minus alpha beta bar and x minus alpha bar beta, both of them divided by K. And then if you multiply this out, what do you got? You got x squared. The coefficient of x is alpha beta bar plus alpha bar beta, all divided by k times x, and then plus alpha bar beta bar divided by k squared equals to 0. Well, the equals to 0 there, when is that equal to 0? Yeah, maybe forget about this equals to 0. Let's not do that. Let's give this thing a name. Let's call this p of x, right? And observe, note, p of alpha beta bar over k is equal to 0, and p of alpha bar beta over k is equal to 0. Now that shows that alpha beta bar over k and alpha bar beta over k are quadratic integers if what condition is met for p. Yeah, we need that they have z coefficients, right? And so how do I know that? Well, I mean, is the coefficient of x squared an integer? Well, yeah, okay, that one I got. So I can vouch for this one, I'm pretty sure. But we need that too. It needs to be monic, right? Coefficient's 1. How do I know that alpha beta bar plus alpha bar beta over k is it? Well, hey, that was divisible. I mean, k is a common divisor of this, right? So that means that you can write alpha beta bar plus alpha bar beta, I should give this stupid thing a name, as a multiple of k, right? So the k cancels and you're just left with an ordinary integer. And likewise for the last piece. So there you go. That proves that this and that are in the ring, in fact, of quadratic integers, and therefore the conjugate ideal has the reverse containment, and it follows, the theorem follows k is equal to AA bar. So we want it.
So you did all that last section just to make sure that that if statement was true?
Yes. Well, but yeah, the last bit is to verify the, precisely. So this is if that condition is met by this, supports that actually being true.
Okay.
And this,
Follows from the end.
and plus that, together gives you equality. Yeah. All right. This point. I want to make sure I have time to do the calculation at the end of the chapter, so I'm going to project a few of these things here. The proofs I'm projecting, they're not difficult. And I think I've written enough detail here that you'll understand what we're doing, so we'll see. Order is shipped. Woo-hoo. All right. Oh, don't look at my order number. Oh no.
What did you order?
Well, I got a laptop from Walmart, and then Dr. Wang told me that it was trash, so I had to take it back. But he didn't say it was trash. He just said it was tragically slow, and he couldn't fix it from all the bloatware which Acer put on it. Not exactly his words, but I'm translating.
No pun intended.
All right, so, and I of course will post this as soon as I can. But anyway, here's the next one, section 12.5, divisibility and containment. So there's two major theorems. And so basically he just finally makes good on these slogans that we've been introducing, like we can replace containment with divisibility, right? So here's the details. If A, B, and C are non-zero ideals, if AB contains AC, then B contains C. So this would be analogous to what we had at the start of the course, where if we had A non-zero, if AB divides AC, that implies that B divides C, right? That was a theorem we had about divisibility early on. Now that's true for containment. That's one thing. So the proofs are based on that conjugate thing we just did, all right? So to start with, he'll prove it for a principal ideal. So suppose A is principal, right? Then A is generated by a single element. So what that means is that if AB contains AC, that means the ideal generated by alpha times B contains the ideal generated by alpha times C, right? What does that mean? That implies that alpha B contains alpha C. I'll prove that in the lemma below. I don't think this is immediately obvious, but it's essentially the same argument I showed you guys last time to fill in the detail in another proof we gave. So we'll look at that in just a second by the lemma. And then once you know that, well, alpha is non-zero, so that implies that beta B contains C. Alpha being non-zero, you can divide elements in alpha B and alpha C by alpha, and you get that any element any element in alpha C being an element in alpha B clearly implies that any element in C is an element in B just by dividing by alpha. So it's really not much to do there. Okay, so once you have it for principal ideals, setting aside the lemma for just a second here. Once you have it for principal ideals, then you can say, well, suppose A is in principal, but it's inside a quadratic imaginary field. So what I can do is I can take AB contained in AC, multiply the thing by A bar, multiply by the conjugate ideal. Once I do that, you see A bar by this little argument we just went through. It's a principal ideal generated by an integer, right? But then k is not equal to 0, so you can divide by k essentially. Yeah. Well, I mean, going back to the argument that I just lost, essentially with k being equal to the alpha, that implies this, which is what we set out to prove. So the only thing that's really left to show was that one thing I jumped with the lemma. And here's the lemma. So for B and C not 0, ideals, and alpha, an element of the R, non-zero, if the product of the ideal, principal ideal generated by alpha times B is contained in the principal ideal generated by alpha times C, then alpha B is contained in alpha C. You'll recognize this proof from last class, or the class before, I forget which one. But what I do is I look at it. Remember, the product of two ideals is defined to be the sums of the products, right? So if A is generated by alpha, that means that AJ is something like, a typical thing in here is something like alpha to the mj power for some natural number. I'm going to assume that the sums we're looking at are non-zero to keep it interesting. The reason I do that is because if they're non-zero, I can always factor an alpha out of every term. So if I look at Z in here, it's something like this. But assuming that these are non-zero terms, there's always at least one copy of alpha in each one of these. So I can just rip it out, and I'm left with some linear combination of ring elements times B's, but B's an ideal. So this is absorbed back in B again. And so I have alpha times something in B, but that by definition is an element of the form alpha times B. When I write alpha B, that just means multiply all of the elements in B by alpha. That's what that notation means. And that's the step I used. Now, Stillwell doesn't have these details in his proof, so I added them because I thought they might be of interest. Or maybe there's some stupid reason that you could say that that's true without my lemma. I don't know. I'm not an expert in these things. I could be making things more complicated than they need to be. If you see a more logical path, which is more efficient than this, let me know. So, of course, the other direction, you also have to prove that this is contained in that, but that's a little bit easier. I'm going to go on before I start coughing. Thank you, Sharon.
I thought you said you were going to stop.
Okay, so again, the calculational theme here is that multiplying by the conjugate, A bar for A makes A bar principal, and this is a nice trick. But it's better than that even because it's not just a principal ideal. It's a principal ideal generated by an integer, which is pretty awesome. So here's the other theorem. Contains means divides. Okay, so we keep coming back to this and what follows. If A and B are ideals, all right, and B contains A, then B divides A in the following sense. What does that mean, B divides A as ideals? That means that there exists another ideal C for which A is equal to a multiple of C in terms of products of ideals. If I showed you this, at the start of the course, and you didn't know about all the other stuff we're doing, you'd just be probably, if you were just kind of like not paying super close attention, didn't notice the containment bit, you'd just be like, yeah, that was our definition of divisibility, so what are you trying to say? The thing that's new here, right, is I'm actually defining divisibility in terms of a product of ideals. So, and we have said this before, but now I'm saying it again. And here's the proof that this makes sense. If B contains A, well, again, begin with the case B is principal, all right? So if B is principal, that means B is equal to, is generated by beta for some ring element beta. So if B contains A, means that the ideal generated by beta contains A. But that means A is a subset of this, right? I mean, just to turn it around. And what is this? What is the ideal generated by beta? It's nothing more than ring multiples of beta, right? Beta R, such that R is in the ring. What does that mean? Think about this. If A is an element of A, that means that A is also an element of this set, right? That means that A is equal to beta R for some R. So what's that mean? If A, everything in A, little a, is equal to beta R for some R, that means that beta divides A for each A in the set A. So beta divides A for each A in A.
Does that mean that beta divides big A?
No. I mean, we don't define divisibility of an element. You could say that, but I haven't defined that concept of divisibility of, I mean, that would be the natural definition, I think, for what would we mean by an element divides a set. I would hope that means that the element divides every element of the set. I mean, that's one interpretation, maybe. But I don't think we've ever defined that. So, but anyway, A is equal to, well, if you look at this, so, I mean, I have A is equal to beta R, right? So I can write then A is equal to a multiple of beta, right? Times R, where R is what? How is R formed? R is equal to A over beta. Right? And then you can argue this is an ideal. That detail's missing from my notes. It's probably worth doing. He has a couple sentences there about why that's an ideal, but rest assured that this thing in parentheses is an ideal, and then that shows that you have A is equal to BC, at least in the case B is principal. And then what does he do? How about it for a general B? What do? You multiply by the conjugate B bar. So continuing here, if B contains A, then B bar B contains A B bar, but B bar B is generated by K for some integer by that stuff. But then what? That means that by the special case we just proved above, in the in the case that in the case that B is in the case that this is the principal ideal contains that, it then follows that this is equal to the principal ideal times some ideal C. So I'm just using the special case to go from here to here. K was played by the role of beta in the previous argument, and we showed that if beta contains another ideal, A B bar, then this ideal can be written as that ideal times some other one. So this A B bar is playing the role that A did in the previous argument. All right. So this is like that. This is like that. So we got A is BC. Here we get this is equal to BC. And then, but we know that K is B bar B, right? And we just proved the cancellation property, right? We proved that if you have non-zero ideals, B and B bar, then you can cancel them, and then there you go. So what this proves is that containment implies divisibility in the natural sense. In other words, if B contains A, that's meaning essentially that B divides A, which more precisely means that A can be written as a multiple of B in terms of a multiple product, a product of ideals. So A is equal to BC for some C. Yes?
Before you go on, how, I know you explained it, but how did it go from K is or AB is a subset of K to AB bar equals KC?
That's using this argument, the previous argument for principal ideal, where we proved that if you have a principal ideal like generated by beta containing A, then that implies A is equal to BC. So like A is, substitute AB bar for A, substitute K for beta in the previous argument. Yeah. These arguments are kind of slick. I think if I tried to attack it directly, it would have been much more cluttered. Like if you tried to do all of the logic of this in this notation, it would have been good. No. These arguments nice. And that brings us to factorizations of ideals. This is a wonderfully simple section. And so let me just, if you go back to the start of this course, we talked about prime factorizations of integers, right? And basically you've known what to do since you were a child, right? You pick a number, any number, 75. To find this prime factorization, you start looking for divisors, right? So, 25 times 3 is 75, right? 3 is prime, you can't break that down further. 25 is 5 times 5. 3 times 5 times 5. None of those can be broken down further. So I take 75, and I broke it into smaller numbers, right? So our prime factorization numbers is based on breaking a number into smaller and smaller numbers. So the interesting thing is, now that we're working with ideals, the tables have kind of turned. We proved last time that prime ideal in the ring of quadratic integers over an imaginary quadratic, the ring of integers over an imaginary quadratic field, we proved prime if and only if maximal, right? Prime is kind of funny. It's a somewhat, prime is defined essentially by the prime divisor property, right? An ideal with prime is what? If P contains a product AB, that implies either P contains A or P contains B, right? That was a prime divisor. That makes P a prime ideal. That's somewhat technical to sort through, right? Maximal, though. Maximal is easy to think about. So we proved that a prime ideal is prime only, an ideal is prime if only if it's maximal. Maximal ideal means what? You can't find a larger ideal that contains the given ideal unless it's the whole ring, right? So this idea of maximal ideal is easy enough to check, right? To show something's maximal, all you have to do is show that if you adjoined anything outside that quote-unquote that proposed maximal ideal, if you pick any element outside the maximal ideal, then adjoining that element forces you to get the whole ring. Right? This is how we proved maximal. We showed that when we adjoined an extra element, we ended up getting the number 1. Consequently, once we get 1, we generate the whole ring, right? That was our argument a couple times. So my point is maximal is easy to think about. So if we start with an ideal and we want to think about factoring it, we want to factor it into prime ideals, right? But prime ideals are maximal. So essentially you're looking for, you take a given ideal and if you can factor it into 2 other ideals, those ideals have to be what? They have to be like larger ideals, right? But the point is, once you factor it, if those can be factored further until to smaller, if you can further factor the product further, you're getting ideals which are larger and larger. But this has to terminate somewhere because you can only get an ideal which is so big before you get the whole ring. So our idea of dividing numbers up into smaller and smaller has been replaced with finding ideals which are larger and larger. But still, there's an end to that, right? Because when you look at ideals, there's only as many, how many different representatives of ideals do you have? You have I plus R, right? But that's a finite number of things, right? So this process has to terminate. That's essentially the guiding logic here. Every non-zero ideal is a product of prime ideals. So here's the argument. Proof. If A is not prime, then it's not maximal. If it's not maximal, that means that there is something that is outside B, right? Which means you can pick an ideal which contains that point outside A. So there's some larger ideal, B, which is not the whole ring, which contains A, right? But what does that mean? B contains A, which means B divides A, which means that you can write A is equal to BC, by what we were just talking about. By containment means divides, right? So you have A is equal to BC, right? Where B is a larger ideal than A was. Then what do? Either C is prime and you can stop, or C is not prime and you can repeat this argument. Or B could be prime, so you stop with that, or it's not prime and you repeat this argument. And you just keep splitting these into products of ideals as long as they're not maximal, right? Any ideal there, either B or C. If either B or C is maximal, you stop. If it's not maximal, make it bigger. Split it into a product of ideals which may or may not be maximal. And you just keep doing this, but it has to terminate a finite order because eventually you're going to get to the whole ring. Yeah.
So like even
Well, or you're going to get to an ideal which can't get larger without making it the whole ring, I should say. Yeah.
so like if B is maximal even though C is not, you stop.
You stop working on that one.
Okay.
But I mean, it's just like primes, right? My example 75, 3 times 25, right? Once I know 3 is prime, I stop working on
Stop
that,
it, you work on
and I
it.
focus on the other thing. Same thing here. But this is a finite process because there's only so many elements that you can adjoin to an ideal to make it larger before you run out of things. There's only a finite number of classes. Uniqueness of the factorization. Any non-zero ideal is unique up to the order of the factors. If you go back to page 29 in the book, it was the prime divisor prop. So what we did was we took 2 integers, we supposed they had a prime factorization, like P1 through PR and Q1 through QS or something like that. And then we just used the prime divisor property to prove that those lists of primes had to be matching by repeated application of the prime divisor property. So if you have the prime divisor property, you can prove uniqueness. So it suffices, by the same argument, just with ideals instead of numbers. So it suffices to prove the prime divisor property. Why do we have the prime divisor property? Right, so this makes P a prime, right? If P contains AB, then P contains A or P contains B. But what does this mean? P contains AB means what? Right, P divides AB. It means P is equal to ABC for some C. P contains A means P is equal to what? Or rather A is equal to PC1 for some other C1. It means B is equal to PC2 for some C2. So we have the prime divisor property by contains means divides. Yeah. Don't worry, I'm not really going to cover section 12.7. It's probably simple. My mind hasn't clicked around his geometric argument just yet, but he draws a picture and basically argues, in this very specific example, z adjoining square root of minus 5. The rest of today we're just talking about z adjoining square root of minus 5, okay? Everything I said up till now would help for a pretty much arbitrary ring of integers over some imaginary quadratic field. Now we're just talking about z adjoining square root of minus 5. So in z adjoining square root of minus 5, there are 2 kinds of ideals. There's the whole thing, right? And then there's this other, and then there's the whole thing which is not principal, right? Z adjoining square root of minus 5 is not a principal ideal. And then there's principal ideals that you can find inside there. So you have these 2 kinds. They have different shapes, right? One is like rectangular in some sense. The other one is more, what was it? I don't know. I forget that we've looked at the shapes before, I forget, but the point is there are only 2 different shapes. This means that the class number of z adjoining square root of minus 5 is 2. So that's kind of a that's what's, I mean, that's, honestly, the notion of class number is a little bit beyond this course, all right? You're seeing an example of it, but we certainly don't have the tools to investigate this question in general. Here's a little bit of the history of the question. In 1773, Lagrange introduced essentially introduced the discussion by trying to reduce by quadratic forms in terms of some bias. So basically, are two quadratic forms equivalent or inequivalent, you know? And so he looked at some sort of binary question, basically amounting to the determinant of something being 1 or positive or something. I don't know. There's not quite nothing there. It's still up for me to parse what he's saying. It's probably fair. I just can't read. And then in 1801, Gauss extended that a bit to negative determinant ones. So, because they're both looking at quadratic forms, right? The question of whether two quadratic forms are inequivalent, whether their matrices are similar under a particular kind of similarity transformation. Again, our homework bombed on that topic. My apologies. And then in 1839, Dirichlet used something called L-series, which, of course, were introduced by Euler. Yes, Euler. So annoying. The L-series are a generalization of zeta functions. The zeta function, do you know what the zeta function is, guys? So zeta function has to do with those, for example, the, I can't do zeta, yeah. So zeta of 2 is what?
That's all right.
Right, but it's, what is it? It's the sum n equals 1 to infinity. 1 over n squared, yeah. So this, for example, would be pi squared over 6. So generally speaking, the zeta function of S, and this is not all there is to say, there's all kinds of issues in terms of what's known as analytic continuation. There's some really deep math here. There's lots of open questions, interesting open questions. Analytic number theorists are obsessed with understanding this thing. Anyway, this L series was some sort of generalization of this animal. You come into contact with this in calculus too a little bit, right? But Dirichlet used these L series to say something about class number. He also solved that arithmetic progression problem that was mentioned back in section 9.9. Anyway, getting more to the point. And then people use these things called modular functions. A modular function in the complex plane is something that satisfies this identity. You might recognize this as a fraction linear transformation. I do believe that is the formula for a Mobius transformation. So there's something to do with these sort of conformal transformations being invariant under J of some sort of another, something like that. Anyway, J is a function of lattice shapes, basically. So you can then, as Kronecker did in 1857, observe that the class number of the imaginary quadratic field is actually the degree of this modular function. So that actually gives you some sort of technique to calculate class number. In particular, you can calculate that the modular function of I is 1728, which is an interesting number because it's one less than that number for Ramanujan, right? 1729, the least number that's the sum of 3 cubes. But anyway, 1728, this is of course an ordinary integer, has degree 1 as an algebraic integer, which goes to show you that the Gaussian integers have just one ideal shape. As we saw, every ideal in the Gaussian integers is principal, right? In fact, that was also true for what? Z joined square root minus 2, but not Z joined square root minus 3, right? Because we had to go to the Eisenstein integers.
And not Z joined square root minus 1, because it has 2 shapes?
Yeah, Z minus 5, this would work out to 2 somehow. He doesn't tell us what J does not tell us what J of the square root minus 5 is. Rest assured that's beyond this course, all right? So if you want to study more about this whole machine we're starting to bump into in terms of these modular functions and further study of quadratic forms, the book you might want to look at is Cox's book. I think it's just primes of the form x squared plus y squared or something like that, or x squared plus my squared. Anyway, I put it on the book list, so that should be in the library, if not already, sometime soon. Anyway, I remember that this book made Spencer very happy. I was forced to listen to tales from it on the way to my car many times. I didn't understand what he's saying, but he was excited about it, so I was happy.
So that would be in the library just because you want it to be?
Well, we put a library about it, and then they say, it's like, what books do you guys want? And I'm just like, no one says anything. So then I say, okay, so I'm just going to go to the list of books from AMS and Springer and just give them a list. So like last Thanksgiving, I gave the math secretary a list of about, I don't know, $10,000 worth of books. We're buying 5,000 of them each year.
Wow.
Yeah.
And where will
libraries-
they be?
What?
They'll be in the library?
Yeah.
Like the JFL library?
Yeah.
No, the JFK library.
We're gonna have lots of books over there. I pretty much bought every standard Springer yellow book that was on some topic that seemed marginally mainstream, and not somebody's,
Is that in the department budget or the library budget?
Well, I don't know what that means. I mean, the library says you guys have $5,000 to spend. If you don't spend it, it just goes into some,
Black hole?
I don't know, maybe it goes into CFA decorating. I don't know. Let's make sure we spend that money on math books. I mean, So I feel like it's my job to make sure that we spend all of our money every year. I mean, if somebody else wants to propose books, I'm not opposed, but some do. The board is about to do books less.
No.
It's a good suggestion here. You should think it's
All right, so finally,
Thanks.
so excuse me. Primes of the form x squared plus 5y squared. We've classified primes of the form x squared plus y squared, x squared plus 2y squared, a few other things, right? X squared plus 3y squared. These can be classified by the things we did before, right? But the Euler and other people a lot smarter than me ran into trouble with this x squared plus 5y squared precisely because z h squared minus 5 is not a principal ideal. So the unique factorization fails, right? Unless we lift to the concept of ideals. Once we generalize our notion of what we're doing to ideals, all of a sudden we can do the calculations. All right, so let's kind of see how that goes. So there's a couple of observations that I'll just start with and I won't justify. You guys have done enough thinking this week. You can read Stillwell, he explains the details, but two things. One, a prime of the form x squared plus 5y squared has to have the form 20n plus 1 or 20n plus 9. This just follows from modular arithmetic. In analyzing modular arithmetic on x squared plus 5y squared. All right. The other thing is if we use quadratic reciprocity, you can prove that minus 5 is a square mod p when p is equal to 20n plus 1 or 20n plus 9. So we do have that primes of that form are squares. Minus 5 is a square mod. Mod p. So then, this is the main theorem. Primes of the form x squared plus 5y squared are precisely those that are primes of the form 20n plus 1 or 20n plus 9. What was the corresponding result for the Gaussian integers? We had primes of the form x squared plus y squared or the form what? Precisely those of the form 4n plus 1. Right? That was it. That's chapter 6 in a nutshell. Right. That's what we got from it. Well, besides awesome homework problems, of course. Yeah. Sharon's I'm going to steal Sharon's book. Shall I read your quote?
I mean, I made it up, so it's pretty amazing. Please.
Ma.
Man.
Oh man, I thought it said ma. It's more funny if you read it as ma. Ma, did you just cut off my
Trunk.
trunk? What, cut my trunk off because I'm dumb. I think if you change the man to ma, it'll all fine. Could be wrong.
If I were an egg, it'd already be hatched because I cracked myself up.
No.
Why?
I blame your parents.
You shouldn't be.
It all goes back to her name. Her name gives her power to respond.
Want to share?
Some sort of.
Share and joy.
Sharon, both your jokes have been recorded.
You're welcome.
That's right.
I got copyright though, okay?
Jokes have been recorded.
I was gonna go into Valentine's Day card making, but I decided not to.
All right, so it remains to show that primes of the form 20n plus 1 and 20n plus 9 are the form x squared plus y squared. What have you done to this book?
No, it's not my fault.
No.
It's Stillwell's. Or
So-
the painter guy.
Did you find it?
Yeah. Aaron's did, Chris's did. Anybody else? Daniel?
I did.
That shows that we are in the book.
Oh, yeah.
All right, so if p,
How did you know?
Did you show
since
me?
p divides m squared plus 5, m squared plus 5 is equal to what? M plus square root of minus 5 times m minus the square root of minus 5. All right. And he says, however, p does not divide either m plus square root of minus 5 or m minus the square root of minus 5. No, it's not. But p does not divide m plus or minus the square root of minus 5 in z between the square root of minus 5. Since, as he says, m plus or minus the square root of minus 5 divided by p divided by p is not an element of z joined to minus 5. However, by the unique prime ideal factorization in z joined to square root of minus 5, follows, right, that the ideal generated by p is not a prime ideal. So what does that mean? Thus, in factors, right? So how can it factor? Right? So he says the easy case is when one of the factors is a principal ideal. So suppose that one of the factors is a principal ideal, something like p, the prime ideal. It factors as, let's say, a plus b times the square root of minus 5 times some other ideal c, where c is a non-trivial ideal. Right? Well, if you take conjugates, what do you get there? If we conjugate this, what do we get? We get, what's the conjugate of p? P is a real prime, right? So the conjugate of the left-hand side is just p again, right? What's the conjugate of this? Well, it's a minus b squared minus 5, right? MC conjugate. And then what? So we've got these two factorizations of p. If you multiply the equations, which is something we can take the product of these two ideals, right? So this tells us that p with p, which is, by the way, p squared, is equal to these guys, right? So a plus b squared of minus 5 times a minus b squared of minus 5 times cc bar. Now what can we do with that? Well, this simplifies, right? What's this simplify to? This simplifies to a squared plus 5b squared. Admittedly, there's a little bit of jump there. And how about CC bar? What is that? Sorry. I'm gonna put this away. I'm not even using this anymore. Let me put this away right here. I'm sorry. What's CC? I mean, CC bar is a product of the ideal and its conjugate, right? That's just the ideal generated by k for some integer k, right? So, hence, p squared is equal to a squared plus 5b squared. I'll write it again, CC bar, but that's equal to a squared plus 5b squared times k. Right, by section 12.4 we started with today. Okay, then what? But what's that tell us? That actually implies that p squared is equal to a squared plus 5b squared times k. For some k. But what does that say k has to be? Yeah, p is prime, right? So I think that forces k to be 1. So, oh, I'm sorry. Oh, I'm an idiot. No. If p squared is equal to this times that, right? That means that what? So he says that implies p is equal to a squared plus 5b squared, actually. I think he's going back to the basic divisibility theory for primes and the integers there. We have.
Does that mean that p equals k?
Let's see, if p squared is equal to the product of a squared plus 5b squared times k, that means p divides a squared plus 5b squared, or p divides k, right? P divides k, there's still another p left over.
The other way around is
Oh, that's
squared
right.
plus 5b squared.
Oh, I'm sorry.
They have to either be 1p or p squared,
Oh, that's right.
but they can't be 1 or p squared.
Let me write that down. So you're like a squared plus 5b squared divides p squared. Okay. Which implies that a squared plus 5b squared is equal to either p minus p or 1. Well, plus or minus 1, right?
Or plus minus p squared.
Oh, plus or minus p squared. Plus or minus p squared? Well, it divides p? No.
That's p squared.
P squared. So how do we get that it's equal to p then?
Because so that p is a not a prime ideal, so I don't know. There's like homework on this, but just with like integers, so I'm not sure if it's the same thing. Because you could say that like, well, if it's not prime, but it has factors, this norm is not equal to 1, and it's not equal to the norm of p. So, and a squared plus.
Well, I know we're short on time, but I think there's a simple argument to make here. But the larger point is, whatever the argument is it's probably something. Whenever I get stuck up a bit like this, it's always something really silly, and I regret it later. But the point is, once you have that, what you've shown is what? The prime has the form x squared plus 5y squared. In this one case, what's the other case? So there's really only another case to think about, The harder case, he says, is where the factors of P are non-principal ideals of the form, the other case would be P is equal to alpha comma alpha times 1 plus the square root of minus 5 divided by 2 times C. And then he has, the argument's on page 235, it's much the same. He conjugates, he takes the product of P and the conjugate ideal, and he then argues that he again gets to this, conjugates, and then he gets to P squared. He gets to P squared is equal to, sorry, let me get to the point. He gets to 2P squared details. 2P squared is equal to A squared plus 5B squared times K. And then he looks at some modular arguments to again imply that P is equal to A squared plus 5B squared. So the point is, in the two different cases which are possible for the ideal factorization of a prime in Z joined to the square root minus 5, in both cases, when you multiply that ideal times its conjugate and work out the details in terms of these ideal calculations, you can prove in both cases that the prime has the form x squared plus 5y squared. I've been a little bit sketchy on the details, of course, but they're all on page 234. So I'll let you look at them. That's all I have for you guys this semester in terms of this book. What?
So what does that mean? Thursday is going to be a massive reveal.
Thursday we'll do fun things like all the stuff I didn't cover.
Really?
Oh, review?
Review.
Please review.
We have a.
But I forgot what we did at the start.
Let's have an interview. We have a test review on Tuesday. Are you going to write a test thing like you did last time? Because that was super helpful.
I will try.
Don't tell them it was helpful. What about an end of the year party?
Kind of might help.
Oh, end of the year party? We might be able to do that.
I can bring my pancake skillet.
I don't think
Breakfast, anyone?
I don't think we can record that. I don't know what you're talking about eating in the classroom.
We can't eat.
That could be in here.